oval body group, on the other hand, has 4 non-write-offs but 2 write-offs. This step is simply a direct application of the attribute selection ideas presented earlier. Let's consider this split to be the one that yields the largest information gain. This simple split into 2 groups reveals the elegance of tree induction and why it resonates well with so many people. The oval body and rectangular body subgroups are simply smaller versions of the problem with which we initially were faced. We can simply take each data subset and recursively apply attribute selection to find the best attribute to partition it. So in our example, we recursively consider the oval body group. To split this group again, we now consider another attribute, head shape. How good is this partitioning? Each of our 2 new groups has a single target label, 4 non-write-offs, all with square heads, and 2 write-offs, all with round heads. These groups are maximally pure with respect to class labels, and there is no need to split them further, according to body color. We still have not done anything with the rectangular body group from our first split, so let's consider how to separate them. In the rectangular body group, there are 5 write-offs and 1 non-write-off. There are 2 attributes we could split upon: head shape, square or round, and body color, white or gray. Either of these would work, so we arbitrarily choose body color. This produces 2 groupings, 5 write-offs in the white body group and 1 non-write-off in the gray body group. These are pure groups, all of one type, so we are finished. In summary, the procedure of classification tree induction is a recursive process of divide and conquer, where the goal at each step is to select an attribute to partition the current group into subgroups that are as pure as possible with respect to the target variable. We perform this partitioning recursively, splitting further and further until we are done. We choose the attributes to split upon by testing all of them and selecting whichever yields the purest subgroups. When are we done? In other words, when do we stop recursing? It should be clear that we would stop when the nodes are pure, or when we run out of variables to split on. But we may want to stop earlier. We will return to this question in Chapter 5. Visualizing segmentations. Continuing with the metaphor of predictive model building as supervised segmentation, it is instructive to visualize exactly how a classification tree partitions the instance space. The instance space is simply the space described by the data features. A common form of instance space visualization is a scatter plot on some pair of features, used to compare one variable against another to detect correlations and relationships. Though data may contain dozens or hundreds of variables, it is only really possible to visualize segmentations in 2 or 3 dimensions at once. Still, visualizing models in instance space in a few dimensions is useful for understanding the different types of models because it provides insights that apply to higher dimensional spaces as well. It may be difficult to compare very different families of models just by examining their form. For example, a mathematical formula versus a set of rules, or the algorithms that generate them. Often, it is easier to compare them based on how they partition the instance space. For example, say we have a simple classification tree for write-offs. The tree's root node tests the balance attribute against a threshold of $50,000, and both of the branches, balance greater than $50,000 and balance less than $50,000, lead to age nodes. The age node on the less than $50,000 side splits into under 50 and over 50, while the age node on the greater than $50,000 side splits into under 45 and over 45. The tree ends with 4 leaf nodes, each giving the number of write-offs in that branch. We can rearrange the data in this tree to create a 2-dimensional graph of the instance space, with balance on the x-axis and age on the y-axis. In the graph, we create lines that give us 4 boxes, representing our groups. The branching of the balance root node corresponds to a vertical line at 50,000 on the x-axis, splitting the plane into balance less than $50,000 and balance more than $50,000. To the left of this line are the instances whose balance values are less than $50,000, most of which are write-offs and a couple of which are not. To the right of the line are the instances whose balance values are greater than $50,000. Here, there are fewer write-offs than not. The next node in our classification tree tests the age attribute against the threshold 50. In the graph, this corresponds to a horizontal line at 50 on the y-axis. This line appears only on the left side of the graph because this partition only applies to examples with a balance of less than $50,000. The second split reveals that nearly all of the write-offs with a balance below $50,000 are younger than 50, while the two non-write-offs with a balance below $50,000 are older than 50. On the right side of the graph, as per the classification tree, age is split at 45 on the y-axis. This split reveals that all of the write-offs with a balance above $50,000 are younger than 45, whereas nearly all of the non-write-offs with a balance above $50,000 are older than 45. Thus, each internal decision node corresponds to a split of the instance space. Each leaf node corresponds to an unsplit region of the space, a segment of the population. Whenever we follow a path in the tree out of a decision node, we are restricting attention to one of the two or more subregions defined by the split. As we descend through a classification tree, we consider progressively more focused subregions of the instance space. Decision lines and hyperplanes. The lines separating the regions are known as decision lines in 2 dimensions, or more generally, decision surfaces or decision boundaries. Each node of a classification tree tests a single variable against a fixed value, so the decision boundary corresponding to it will always be perpendicular to the axis representing this variable. In 2 dimensions, the line will be either horizontal or vertical. If the data had 3 variables, the instance space would be 3-dimensional, and each boundary surface imposed by a classification tree would be a 2-dimensional plane. In higher dimensions, since each node of a classification tree tests one variable, it may be thought of as fixing that one dimension of a decision boundary. Therefore, for a problem of n variables, each node of a classification tree imposes an n-1 dimensional hyperplane decision boundary on the instance space. You will often see the term hyperplane used in data mining literature to refer to the general separating surface, whatever it may be. Don't be intimidated by this terminology. You can always just think of it as a generalization of a line or a plane. Other decision surfaces are possible, as we shall learn later. Trees as sets of rules. Before moving on from the interpretation of classification trees, we should mention their interpretation as logical statements. With classification trees, you classify a new unseen instance by starting at the root node and following the attribute tests downward until you reach a leaf node, which specifies the instance's predicted class. If we trace down a single path from the root node to a leaf, collecting the conditions as we go, we generate a rule. Each rule consists of the attribute tests along the path connected with and. Consider the simple classification tree used in our earlier example. Starting at the root node and choosing the left branches of the tree, we get the rule: if balance is less than 50,000 and age is less than 50, then class equals write-off. We can do this for every possible path to a leaf node. From this tree, we get 3 more rules. If balance is less than 50,000 and age is more than 50, then class equals non-write-off. If balance is greater than 50,000 and age is less than 45, then class equals write-off. And if balance is greater than 50,000 and age is less than 50, then class equals non-write-off. The classification tree is equivalent to this rule set. If these rules look repetitive, that's because they are. The tree gathers common rule prefixes together toward the top of the tree. Every classification tree can be expressed as a set of rules this way. Whether the tree or the rule set is more intelligible is a matter of opinion. In this simple example, both are fairly easy to understand. As the model becomes larger, some people will prefer the tree or the rule set. Probability estimation. In many decision-making problems, we would like a more informative prediction than just a classification. For example, in our churn prediction problem, rather than simply predicting whether a person will leave the company within 90 days of contract expiration, we would much rather have an estimate of the probability that he will leave the company within that time. Such estimates can be used for many purposes. We will discuss some of these in detail in later chapters, but briefly, you might then rank prospects by their probability of leaving, and then allocate a limited incentive budget to the highest probability instances. Alternatively, you may want to allocate your incentive budget to the instances with the highest expected loss, for which you'll need an estimate of the probability of churn. Once you have such probability estimates, you can use them in a more sophisticated decision-making process than these simple examples, as we'll describe in later chapters. There is another, even more insidious problem with models that give simple classifications rather than estimates of class membership probability. Consider the problem of estimating credit default. Under normal circumstances, for just about any segment of the population to which we would be considering giving credit, the probability of write-off will be very small, far less than 0.5. In this case, when we build a model to estimate the classification, write-off or not, we'd have to say that for each segment, the members are likely not to default, and they will all get the same classification, not write-off. For example, in a naively built tree model, every leaf will be labeled not write-off. This turns out to be a frustrating experience for new data miners. After all that work, the model really just says that no one is likely to default? This does not mean that the model is useless. It may be that the different segments indeed have very different probabilities of write-off. They just all are less than 0.5. If instead we use these probabilities for assigning credit, we may be able to reduce our risk substantially. So, in the context of supervised segmentation, we would like each segment, or leaf of a tree model, to be assigned an estimate of the probability of membership in the different classes. Fortunately, the tree induction ideas we have discussed so far can easily produce probability estimation trees instead of simple classification trees. Recall that the tree induction procedure subdivides the instance space into regions of class purity, low entropy. If we are satisfied to assign the same class probability to every member of the segment corresponding to a tree leaf, we can use instance counts at each leaf to compute a class probability estimate. For example, if a leaf contains n positive instances and m negative instances, the probability of any new instance being positive may be estimated as n divided by the quantity n plus m. This is called a frequency-based estimate of class membership probability. At this point, you may spot a problem with estimating class membership probabilities this way. We may be overly optimistic about the probability of class membership for segments with very small numbers of instances. At the extreme, if a leaf happens to have only a single instance, should we be willing to say that there is a 100% probability that members of that segment will have the class that this one instance happens to have? This phenomenon is one example of a fundamental issue in data science, overfitting, to which we devote a chapter later in the book. For completeness, let's quickly discuss one easy way to address this problem of small samples for tree-based class probability estimation. Instead of simply computing the frequency, we would often use a smoothed version of the frequency-based estimate, known as the Laplace correction, the purpose of which is to moderate the influence of leaves with only a few instances. The equation for binary class probability estimation becomes n plus 1, divided by the quantity n plus m plus 2, where n is the number of examples in the leaf belonging to class C, and m is the number of examples not belonging to class C. Let's walk through an example with and without the Laplace correction. A leaf node with 2 positive instances and no negative instances would produce the same frequency-based estimate, probability equals 1, as a leaf node with 20 positive instances and no negatives. However, the first leaf node has much less evidence and may be extreme only due to there being so few instances. Its estimate should be tempered by this consideration. The Laplace equation smooths its estimate down to probability equals 0.75 to reflect this uncertainty. The Laplace correction has much less effect on the leaf with 20 instances. As the number of instances increases, the Laplace equation converges to the frequency-based estimate. Example: addressing the churn problem with tree induction. Now that we have a basic data mining technique for predictive modeling, let's consider the churn problem again. How could we use tree induction to help solve it? For this example, we have a historical dataset of 20,000 customers. At the point of collecting the data, each customer either had stayed with the company or had left, churned. Each customer is described by 10 variables, including college education, annual income, and average monthly overcharges, among others. These variables comprise basic demographic and usage information available from the customer's application and account. We want to use these data with our tree induction technique to predict which new customers are going to churn. Before starting to build a classification tree with these variables, it is worth asking, how good are each of these variables individually? For this, we measure the information gain of each attribute, as discussed earlier, to see what each gains us. On reviewing the resulting table, which contains the exact information gain values, we find that 3 variables, the house value, the number of leftover minutes, and the number of long calls per month, have a higher information gain than the rest. Perhaps surprisingly, neither the amount the phone is used nor the reported degree of satisfaction seems, in and of itself, to be very predictive of churning. Applying a classification tree algorithm to the data, we get a tree in which the highest information gain feature, the house value, is at the root of the tree. This is to be expected since it will always be chosen first. The second best feature, the number of leftover minutes, also appears high in the tree. However, the order in which features are chosen for the tree doesn't exactly correspond to their information gain ranking. Why is this? The answer is that the table ranks each feature by how good it is independently, evaluated separately on the entire population of instances. Nodes in a classification tree depend on the instances above them in the tree. Therefore, except for the root node, features in a classification tree are not evaluated on the entire set of instances. The information gain of a feature depends on the set of instances against which it is evaluated. So, the ranking of features for some internal node may not be the same as the global ranking. For example, our churn probability tree's house value root node splits into houses worth more than $600,000 on the left and less than $600,000 on the right. It could be that the number of leftover minutes, the second best feature overall, is extremely useful for predicting churn on the left side of the tree, but only somewhat useful for the right side of the tree. Further, we have not yet discussed how we decide to stop building the tree. If the dataset has 20,000 examples, should we create a tree with 20,000 leaf nodes? Can we just keep selecting more attributes to split upon, building the tree downwards until we've exhausted the data? The answer is yes, we can, but we should stop long before the model becomes that complex. This issue ties in closely with model generality and overfitting, whose discussion we defer to Chapter 5. Consider a final issue with this dataset. After building a tree model from the data, let's say we decide to measure its accuracy against the data to see how good of a model it is. Specifically, we use a training set consisting half of people who churned and the other half who did not. After learning a classification tree from this, we apply the tree to the dataset to see how many examples it can classify correctly. Say it achieves 73% accuracy on its decisions. This raises two questions. One, do you trust this number? If we applied the tree to another sample of 20,000 people from the same dataset, do you think we'd still get about 73% accuracy? And two, if you do trust the number, does it mean this model is good? In other words, is a model with 73% accuracy worth using? We will revisit these questions in Chapter 7 and 8, which delve into issues of model evaluation. Summary. In this chapter, we introduced basic concepts of predictive modeling, one of the main tasks of data science, in which a model is built that can estimate the value of a target variable for a new unseen example. In the process, we introduced one of data science's fundamental notions: finding and selecting informative attributes. Selecting informative attributes can be a useful data mining procedure in and of itself. Given a large collection of data, we now can find those variables that correlate with or give us information about another variable of interest. For example, if we gather historical data on which customers have or have not left the company, churned, shortly after their contracts expire, attribute selection can find demographic or account-oriented variables that provide information about the likelihood of customers churning. One basic measure of attribute information is called information gain, which is based on a purity measure called entropy. Another is variance reduction. Selecting informative attributes forms the basis of a common modeling technique called tree induction. Tree induction recursively finds informative attributes for subsets of the data. In so doing, it segments the space of instances into similar regions. The partitioning is supervised, and that it tries to find segments that give increasingly precise information about the quantity to be predicted, the target. The resulting tree-structured model partitions the space of all possible instances into a set of segments with different predicted values for the target. For example, when the target is a binary class variable, such as churn versus not churn, or write-off versus not write-off, each leaf of the tree corresponds to a population segment with a different estimated probability of class membership. Note, as an exercise, think about what would be different in building a tree-structured model for regression rather than for classification. What would need to be changed from what you've learned about classification tree induction? Historically, tree induction has been a very popular data mining procedure because it is easy to understand, easy to implement, and computationally inexpensive. Research on tree induction goes back to at least the 1950s and 1960s. Some of the earliest popular tree induction systems include chi-squared automatic interaction detection and classification and regression trees, which are still widely used. C4.5 and C5.0 are also very popular tree induction algorithms, which have a notable lineage. J48 is a reimplementation of C4.5 in the Weka package. In practice, tree-structured models work remarkably well, though they may not be the most accurate model one can produce from a particular dataset. In many cases, especially early in the application of data mining, it is important that models be understood and explained easily. This can be useful not just for the data science team, but for communicating results to stakeholders not knowledgeable about data mining. Chapter 4. Fitting a model to data. The fundamental concepts discussed in this chapter are finding optimal model parameters based on data, choosing the goal for data mining, objective functions, and loss functions. The exemplary techniques are linear regression, logistic regression, and support vector machines. As we have learned, predictive modeling involves finding a model of the target variable in terms of other descriptive attributes. In Chapter 3, we constructed a supervised segmentation model by recursively finding informative attributes on ever more precise subsets of the set of all instances, or, from the geometric perspective, ever more precise subregions of the instance space. From the data, we produced both the structure of the model, the particular tree model that resulted from the tree induction, and the numeric parameters of the model, the probability estimates at the leaf nodes. An alternative method for learning a predictive model from a dataset is to start by specifying the structure of the model with certain numeric parameters left unspecified. Then, the data mining calculates the best parameter values given a particular set of training data. A very common case is where the structure of the model is a parameterized mathematical function or equation of a set of numeric attributes. The attributes used in the model could be chosen based on domain knowledge regarding which attributes ought to be informative in predicting the target variable. Or, they could be chosen based on other data mining techniques, such as the attribute selection procedures introduced in Chapter 3. The data miner specifies the form of the model and the attributes. The goal of the data mining is to tune the parameters so that the model fits the data as well as possible. This general approach is called parameter learning or parametric modeling. Note, in certain fields of statistics and econometrics, the bare model with unspecified parameters is called the model. We will clarify that this is the structure of the model, which still needs to have its parameters specified to be useful. Many data mining procedures fall within this general framework. We will demonstrate with some of the most common, all of which are based on linear models. If you've taken a statistics course, you're probably already familiar with one linear modeling technique, linear regression. We will see the same differences in models that we've discussed already, such as the differences in task between classification, class probability estimation, and regression. As examples, we will present some common techniques used for predicting, estimating, unknown numeric values, unknown binary values, such as whether a document or web page is relevant to a query, as well as likelihoods of events, such as default on credit, response to an offer, fraud on an account, and so on. We also will explicitly discuss something that we skirted in Chapter 3. What exactly do we mean when we say a model fits the data well? This is the crux of the fundamental concept of this chapter. Fitting a model to data by finding optimal model parameters, and is a notion that will resurface in later chapters. Because of its fundamental concepts, this chapter is more mathematically focused than the rest. We will keep the math to a minimum and encourage the less mathematical listener to proceed boldly. Sidebar: simplifying assumptions in this chapter. The point of this chapter is to introduce and explain parametric modeling. To keep the discussion focused, we've made some simplifying assumptions. First, for classification and class probability estimation, we will consider only binary classes. The models predict events that either take place or do not, such as responding to an offer, leaving the company, being defrauded, and so on. The methods here can all be generalized to work with multiple non-binary classes, but the generalization complicates the description unnecessarily. Second, because we're dealing with equations, this chapter assumes all attributes are numeric. There are techniques for converting categorical, symbolic, attributes into numerical values for use with these equations. Finally, we ignore the need to normalize numeric measurements to a common scale. Attributes such as age and income have vastly different ranges, and they are usually normalized to a common scale to help with model interpretability, as well as other things to be discussed later. We ignore these complications in this chapter. However, dealing with them is ultimately important and often necessary regardless of the data mining technique. Classification via mathematical functions. Recall the instance space, or grid view, of tree models from Chapter 3, which uses horizontal and vertical decision boundaries to partition the instance space into similar regions. Examples in each region should have similar values for the target variable. In the last chapter, we discovered how the entropy measure gives us a way of measuring homogeneity so we can choose such boundaries. A main purpose of creating homogeneous regions is so that we can predict the target variable of a new, unseen instance by determining which segment it falls into. For example, if a new customer falls into the lower left segment of the graph we described in Chapter 3, where balance is less than $50,000 and age is less than 50, we can conclude that the target value is very likely to be write-off, or bad customer. Similarly, if it falls into the upper right segment, where balance is greater than $50,000 and age is greater than 45, we can predict its value as non-write-off, or good customer. The instance space view is helpful because if we take away the axis parallel boundaries, leaving only the data points, we can find other, possibly better, ways to partition the space. For example, we can separate the instances almost perfectly by class if we are allowed to introduce a boundary that is still a straight line, but that goes diagonally from the top left to bottom right of the graph. This is called a linear classifier and is essentially a weighted sum of the values for the various attributes, as we will describe next. Linear discriminant functions. Our goal is going to be to fit our model to the data, and to do so, it is quite helpful to represent the model mathematically. You may recall that the equation of a line in 2 dimensions is y equals mx plus b, where m is the slope of the line and b is the y-intercept, the y value when x equals 0. The diagonal line that nearly perfectly separates the instances by class can be expressed in this form, with balance in thousands, as age equals negative 1.5 times balance plus 60. We would classify an instance X, in other words a customer, as a non-write-off customer if its output falls above the line, and as a write-off customer if it falls below the line. Rearranging this mathematically leads to the function that is the basis of all the techniques discussed in this chapter. The classification of a customer X is non-write-off if negative 1 times age minus 1.5 times balance plus 60 is greater than 0. The classification is write-off if negative 1 times age minus 1.5 times balance plus 60 is less than or equal to 0. This is called a linear discriminant because it discriminates between the classes, and the function of the decision boundary is a linear combination, a weighted sum of the attributes. In the 2 dimensions of our example, the linear combination corresponds to a line. In 3 dimensions, the decision boundary is a plane, and in higher dimensions, it is a hyperplane. For our purposes, the important thing is that we can express the model as a weighted sum of the attribute values. Thus, this linear model is a different sort of multivariate supervised segmentation. Our goal with supervised segmentation still is to separate the data into regions with different values of the target variable. The difference is that the method for taking multiple attributes into account is to create a mathematical function of them. Earlier, we explored how a classification tree corresponds to a rule set, a logical classification model of the data. A linear discriminant function is a numeric classification model. For example, consider our feature vector x, with the individual component features being x1, x2, x3, and so on. A linear model can then be given like this. F of x equals some number plus weighting 1 times feature 1, plus weighting 2 times feature 2, plus weighting 3 times feature 3, and so on. In our example, f of x equals 60 minus 1 times age minus 1.5 times balance. To use this model as a linear discriminant for a given instance represented by a feature vector x, we check whether f of x is positive or negative. As discussed earlier in the 2-dimensional case, this corresponds to seeing whether the instance x falls above or below the line. Linear functions are one of the workhorses of data science. Now, we finally come to the data mining. We now have a parameterized model. The weights of the linear function are the parameters. The data mining is going to fit this parameterized model to a particular data set, meaning specifically to find a good set of weights on the features. After learning, these weights are often loosely interpreted as importance indicators of the features. Roughly, the larger the magnitude of a feature's weight, the more important that feature is for classifying the target, assuming all feature values have been normalized to the same range. By the same token, if a feature's weight is near zero, the corresponding feature can usually be ignored or discarded. For now, we are interested in a set of weights that discriminate the training data well and predict as accurately as possible the value of the target variable for cases where we don't know it. Unfortunately, it's not trivial to choose the best line to separate the classes. Let's consider a simple case where the training data can indeed be separated by class using a linear discriminant. However, there actually are many different linear discriminants that can separate the classes perfectly. They have very different slopes and intercepts, and each represents a different model of the data. In fact, there are infinitely many lines, models, that classify this training set perfectly. Which should we pick? Optimizing an objective function. This brings us to one of the most important fundamental ideas in data mining, one that surprisingly is often overlooked even by data scientists themselves. We need to ask, what should be our goal, or objective, in choosing the parameters? In our case, this would allow us to answer the question, what weights should we choose? Our general procedure will be to define an objective function that represents our goal, and can be calculated for a particular set of weights and a particular set of data. We will then find the optimal value for the weights by maximizing or minimizing the objective function. What can easily be overlooked is that these weights are best only if we believe that the objective function truly represents what we want to achieve, or, practically speaking, is the best proxy we can come up with. We will return to this later in the book. Unfortunately, creating an objective function that matches the true goal of the data mining is usually impossible. So, data scientists often choose based on faith and experience. Several choices have been shown to be remarkably effective. One of these choices creates the so-called support vector machine, about which we will say a few words after presenting a concrete example with a simpler objective function. After that, we will briefly discuss linear models for regression, rather than classification, and end with one of the most useful data mining techniques of all, logistic regression. Its name is something of a misnomer. Logistic regression doesn't really do what we call regression, which is the estimation of a numeric target value. Logistic regression applies linear models to class probability estimation, which is particularly useful for many applications. Linear regression, logistic regression, and support vector machines are all very similar instances of our basic fundamental technique, fitting a linear model to data. The key difference is that each uses a different objective function. An example of mining a linear discriminant from data. To further explore linear discriminant functions, we use an adaptation of the iris dataset taken from the UCI data repository. This is an old and fairly simple dataset representing various types of iris, a genus of flowering plant. The original dataset includes 3 species of irises represented with 4 attributes, and the data mining problem is to classify each instance as belonging to one of the 3 species based on the attributes. For this example, we'll use just 2 species of irises, Iris setosa and Iris versicolor. The dataset describes a collection of flowers of these 2 species, each described with 2 measurements: the petal width, from 0 to 2 centimeters along the x-axis, and the sepal width, from 0 to 5 centimeters along the y-axis. All instances of Iris setosa have a petal width between 1 and 2 centimeters and a sepal width between 2 and 3.5 centimeters, placing them in the upper middle section of the graph. Nearly all instances of Iris versicolor have a petal width between 0 and 0.5 centimeters and a sepal width between 2 and 5 centimeters, placing them predominantly in the lower right section of the graph, aside from one outlier with a petal width of 1 centimeter that places it just left of the Iris setosa. we can split the iris setosa from the iris versicolor with two different separation lines, one generated by logistic regression and the second by another linear method, a support vector machine, which will be described shortly. Logistic regression separates the two classes completely. All the iris versicolor examples are to the immediate left of its line, and the iris setosa further to the right. The support vector machine line is almost midway between the clumps, though it misclassifies the one iris versicolor outlier as an iris setosa. Which separator do you think is better? In Chapter 5, we will get into details of why these separators are different and why one might be preferable to the other. For now, it's enough just to notice that the methods produce different boundaries because they're optimizing different functions. Linear discriminant functions for scoring and ranking instances. In many applications, we don't simply want a yes or no prediction of whether an instance belongs to the class, but we want some notion of which examples are more or less likely to belong to the class. For example, which consumers are most likely to respond to this offer? Which customers are most likely to leave when their contracts expire? One option is to build a model that produces an estimate of class membership probability, as we did with tree induction for class probability estimation in Chapter 3. We can do this with linear models as well, and we'll treat this in detail when we introduce logistic regression later on. In other applications, we do not need a precise probability estimate. We simply need a score that will rank cases by the likelihood of belonging to one class or the other. For example, for targeted marketing, we may have a limited budget for targeting prospective customers. We would like to have a list of consumers ranked by their predicted likelihood of responding positively to our offer. We don't necessarily need to be able to estimate the exact probability of response accurately, as long as the list is ranked reasonably well, and the consumers at the top of the list are the ones most likely to respond. Linear discriminant functions can give us such a ranking for free. Assume we are presented with a new instance X, for which we do not yet know the class. That is, we have not yet made an offer to X. In which portion of the instance space would we like X to fall in order to expect the highest likelihood of response? Where would we be most certain that X would not respond? Where would we be most uncertain? Many people suspect that right near the decision boundary, we would be most uncertain about a class. Far away from the decision boundary on the response side would be where we would expect the highest likelihood of response. In the equation of the separating boundary, f of x will be 0 when x is sitting on the decision boundary. Technically, x in that case is one of the points of the line or hyperplane. F of x will be relatively small when x is near the boundary, and f of x will be large and positive when x is far from the boundary in the response direction. Thus, f of x itself, the output of the linear discriminant function, gives an intuitively satisfying ranking of the instances by their estimated likelihood of belonging to the class of interest. Support vector machines, briefly. If you're even on the periphery of the world of data science these days, you eventually will run into the support vector machine, or SVM. This is a notion that can strike fear into the hearts even of people quite knowledgeable in data science. Not only is the name itself opaque, but the method often is imbued with the sort of magic that derives from perceived effectiveness without understanding. Fortunately, we now have the concepts necessary to understand support vector machines. In short, support vector machines are linear discriminants. For many business users interacting with data scientists, that will be sufficient. Nevertheless, let's consider SVMs a little more carefully. If we can get through some minor details, the procedure for fitting the linear discriminant is intuitively satisfying. As with linear discriminants generally, SVMs classify instances based on a linear function of the features, described by the general linear model equation mentioned earlier. Note: you may also hear of nonlinear support vector machines. Oversimplifying slightly, a nonlinear SVM uses different features, that are functions of the original features, so that the linear discriminant with the new features is a nonlinear discriminant with the original features. So, as we've discussed, the crucial question becomes, what is the objective function that is used to fit an SVM to data? For now, we will skip the mathematical details in order to gain an intuitive understanding. There are two main ideas. Recall our discussion on the infinitude of different possible linear discriminants to separate classes in a dataset. And recall that choosing an objective function for fitting the data amounts to choosing which of these lines is the best. SVMs choose based on a simple, elegant idea. Instead of thinking about separating with a line, first, fit the fattest bar possible between the classes. That is, draw two lines, one line as close as possible to one set and the other as close as possible to the other set, in order to create a rectangle, or bar, of sorts between the two sets. The SVM's objective function incorporates the idea that a wider bar is better. Then, once the widest bar is found, the linear discriminant will be the center line through the bar. The distance between the two lines used to create the bar is called the margin around the linear discriminant, and thus, the objective is to maximize the margin. The idea of maximizing the margin is intuitively satisfying for the following reason. The training dataset is just a sample from some population. In predictive modeling, we are interested in predicting the target for instances that we have not yet seen. These instances will be scattered about. Hopefully, they will be distributed similarly to the training data, but they will in fact be different points. In particular, some of the positive examples will likely fall closer to the discriminant boundary than any positive example we have yet seen. All else being equal, the same applies to the negative examples. In other words, they may fall in the margin. The margin maximizing boundary gives the maximal leeway for classifying such points. Specifically, by choosing the SVM decision boundary, in order for a new instance to be misclassified, one would have to place it further into the margin than with any other linear discriminant, or, of course, completely on the wrong side of the margin bar altogether. The second important idea of SVMs lies in how they handle points falling on the wrong side of the discrimination boundary. We may encounter a situation in which a single line cannot perfectly separate the data into classes. This is true of most data from complex real-world applications. Some data points will inevitably be misclassified by the model. This does not pose a problem for the general notion of linear discriminants, as their classifications don't necessarily have to be correct for all points. However, when fitting the linear function to the data, we cannot simply ask which of all the lines that separate the data perfectly should we choose. There may be no such perfect separating line. Once again, the support vector machine solution is intuitively satisfying. Skipping the math, the idea is as follows. In the objective function that measures how well a particular model fits the training points, we will simply penalize a training point for being on the wrong side of the decision boundary. In the case where the data indeed are linearly separable, we incur no penalty and simply maximize the margin. If the data are not linearly separable, the best fit is some balance between the fat margin and a low total error penalty. The penalty for a misclassified point is proportional to the distance from the margin boundary. So if possible, the SVM will make only small errors. Technically, this error function is known as hinge loss. Regression via mathematical functions. The previous chapter introduced the fundamental notion of selecting informative variables. We showed that this notion applies to classification, to regression, and to class probability estimation. Here too, this chapter's basic notion of fitting linear functions to data applies to classification, regression, and to class probability estimation. Let's now discuss regression briefly. Sidebar: loss functions. The term loss is used across data science as a general term for error penalty. A loss function determines how much penalty should be assigned to an instance based on the error in the model's predicted value. In our present context, based on its distance from the separation boundary. Several loss functions are commonly used. Consider a graph where the horizontal axis is the distance from the separating boundary. In this case, errors have positive distances from the separator, while correct classifications have negative distances. Support vector machines use hinge loss, so called because the loss graph looks like a hinge. Hinge loss incurs no penalty for an example that is not on the wrong side of the margin. The hinge loss only becomes positive when an example is on the wrong side of the boundary and beyond the margin. Loss then increases linearly with the example's distance from the margin, thereby penalizing points more the farther they are from the separating boundary. 0-1 loss, as its name implies, assigns a loss of 0 for a correct decision and 1 for an incorrect decision. For contrast, consider a different sort of loss function. Squared error specifies a loss proportional to the square of the distance from the boundary. Squared error loss usually is used for numeric value prediction, regression, rather than classification. The squaring of the error has the effect of greatly penalizing predictions that are grossly wrong. For classification, this would apply large penalties to points far over on the wrong side of the separating boundary. Unfortunately, using squared error for classification also penalizes points far on the correct side of the decision boundary. For most business problems, choosing squared error loss for classification or class probability estimation, thus, would violate our principle of thinking carefully about whether the loss function is aligned with the business goal. Hinge-like versions of squared error have been created because of this misalignment. We have already discussed most of what we need for linear regression. The linear regression model structure is exactly the same as for the linear discriminant function. f of x equals some number plus weighting 1 times feature 1 plus weighting 2 times feature 2 plus weighting 3 times feature 3, and so on. So, following our general framework for thinking about parametric modeling, we need to decide on the objective function we will use to optimize the model's fit to the data. There are many possibilities. Each different linear regression modeling procedure uses one particular choice, and the data scientist should think carefully about whether it is appropriate for the problem. The most common, standard, linear regression procedure makes a powerful and convenient choice. Recall that for regression problems, the target variable is numeric. The linear function estimates this numeric target value using the equation given earlier. And of course, the training data have the actual target value. Therefore, an intuitive notion of the fit of the model is, how far away are the estimated values from the true values on the training data? In other words, how big is the error of the fitted model? Presumably, we'd like to minimize this error. For a particular training data set, we could compute this error for each individual data point and sum up the results. Then, the model that fits the data best would be the model with the minimum sum of errors on the training data. And that is exactly what regression procedures do. You might notice that we really have not actually specified the objective function, because there are many ways to compute the error between an estimated value and an actual value. The method that is most natural is to simply subtract one from the other and take the absolute value. So if I predict 10 and the actual value is 12 or 8, I make an error of 2. This is called absolute error, and we could then minimize the sum of absolute errors, or equivalently, the mean of the absolute errors across the training data. This makes a lot of sense, but it is not what standard linear regression procedures do. Standard linear regression procedures instead minimize the sum or mean of the squares of these errors, which gives the procedure its common name, least squares regression. So, why do so many people use least squares regression without much thought to alternatives? The short answer is convenience. It is the technique we learn in basic statistics classes and beyond. It is available to us to use in various software packages. Originally, The least squared error function was introduced by the famous 18th century mathematician Carl Friedrich Gauss, and there are certain theoretical arguments for its use, relating to the normal or Gaussian distribution. Often, more importantly, it turns out that squared error is particularly convenient mathematically. This was helpful in the days before computers. From a data science perspective, the convenience extends to theoretical analyses, including a clean decomposition of model error into different sources. More pragmatically, analysts often claim to prefer squared error because it strongly penalizes very large errors. Whether the quadratic penalty is actually appropriate is specific to each application. Why not take the fourth power of the errors and penalize large errors even more strongly? Importantly, any choice for the objective function has both advantages and drawbacks. For least squares regression, a serious drawback is that it is very sensitive to the data. Erroneous or otherwise outlying data points can severely skew the resultant linear function. For some business applications, we may not have the resources to spend as much time on manual massaging of the data as we would in other applications. At the extreme, for systems that build and apply models totally automatically, the modeling needs to be much more robust than when doing a detailed regression analysis by hand. Therefore, for the former application, we may want to use a more robust modeling procedure. For example, using absolute error as the objective function instead of squared error. An important thing to remember is that once we see linear regression simply as an instance of fitting a linear model to data, we see that we have to choose the objective function to optimize, and we should do so with the ultimate business application in mind. Class probability estimation and logistic regression. As mentioned earlier, for many applications, we would like to estimate the probability that a new instance belongs to the class of interest. In many cases, we would like to use the estimated probability in a decision-making context that includes other factors, such as costs and benefits. For example, predictive modeling from large consumer data is used widely in fraud detection across many industries, especially banking, telecommunications, and online commerce. A linear discriminant could be used to identify accounts or transactions as likely to have been defrauded. The director of the fraud control operation may want the analysts to focus not simply on the cases most likely to be fraud, but on the cases where the most money is at stake. That is, accounts where the company's monetary loss is expected to be the highest. For this, we need to estimate the actual probability of fraud. Chapter 7 will discuss in detail the use of expected value to frame business problems. Fortunately, within this same framework for fitting linear models to data, by choosing a different objective function, we can produce a model designed to give accurate estimates of class probability. The most common procedure by which we do this is called logistic regression. Note: what exactly is an accurate estimate of class membership probability is a subject of debate beyond the scope of this book. Roughly, we would like the probability estimates to be well calibrated, meaning that if you take 100 cases whose class membership probability is estimated to be 0.2, then about 20 of them will actually belong to the class. We would also like the probability estimates to be discriminative, in that, if possible, they give meaningfully different probability estimates to different examples. The latter condition keeps us from simply giving the base rate, the overall prevalence in the population, as the prediction for every example. Say 0.5% of accounts overall are fraudulent. Without the latter condition, we could simply predict the same 0.5% probability for each account. Those estimates would be well calibrated, but not discriminative at all. To understand logistic regression, it is instructive to first consider exactly what is the problem with simply using our basic linear model to estimate the class probability. As we discussed, an instance being further from the separating boundary intuitively ought to lead to a higher probability of being in one class or the other, and the output of the linear function, f of x, gives the distance from the separating boundary. However, this also shows the problem. F of x ranges from -infinity to infinity, and a probability should range from 0 to 1. So let's take a brief stroll down a garden path and ask how else we might cast our distance from the separator, f of x, in terms of the